In this video, we're going to talk about conjugate acid-base pairs. Before we dig into that rather intimidating sounding term, let's talk about what we mean by acids and bases. Long ago, centuries ago, scientists discovered acids and bases by their taste and their feel. And while we don't go around tasting substances in the lab, it was long acknowledged that acids are substances that taste sour. Now, on a chemical level, that means that the reason they taste sour is because of a particular ion that they give when they dissolve in water. Bases are substances that taste bitter and they have a slippery feel to them. If you pick up a bar of soap, that's largely a base. And of course, soap is slippery. We have acids and bases in our houses. They're not necessarily dangerous. Vinegar, lemon juice, orange juice, any kind of a soda is typically an acid. Bases include baking soda, Drano drain cleaner, ammonia cleaner, oven cleaner. These are things that we encounter every day. There are lots of different definitions of acids and bases, and if you read a chemistry book, you'll find several of them. There's only one that I really want you to focus on, and it was the one articulated by the Danish scientists Bronsted and Lowry. This is what they said. Acids are substances that donate or get rid of protons. Now, what do we mean by a proton? Picture this, students. A neutral hydrogen atom consists of one proton. At least the most common isotope of hydrogen has just one proton in its nucleus. And if it's neutral, it has one electron. Now, if we were to make that an ion, positively one charged ion, take away that electron, and what do you have left? A proton, just a single proton. So when we talk about proton donors, we're talking about H plus ion donors. Those two things are interchangeable. Bases are substances that accept or receive protons or H plus ions. Hence, whenever there's a reaction that involves an acid, the H plus ion needs to go somewhere. Now, we don't always represent the recipient of the H plus ion in a chemical equation. But if we do, if you write a full acid-base equation, there's got to be a recipient. So acids and bases work together. The point is they're always working together. Okay, now here's the challenge. When we look at a chemical equation, we've got to be able to read it from left to right, just like a sentence in a book. You start on the left side and you end up with the right side. As you do that, remember that acids are the substances donating or losing H plus, and bases are the substances gaining or receiving H plus. So here's an example. If we take hydrochloric acid, HCl, notice that it is originally on the left side of the equation. After donating H plus, what it became was Cl minus. Notice that the two things that are related to each other by the donating and receiving of a proton or H plus ion are connected to each other in some way. We'll talk about what that means in just a moment. The other reactant, the H2O, upon receiving an H plus, became H3O plus. H2O has two hydrogens, H3O has three hydrogens. So one of the reactants lost H plus, that was the HCl, that's the acid. The other reactant gained H plus, that's the base. So we can define the acid and base as the substance that receives an acid, receives in a base is the one that receives an H, and the acid is the one that loses an H. Now, we're not always going to be dealing with hydrochloric acid, so often chemists talk about a general acid. When we say general acid, we write the formula HA. Now, that means hydrogen attached to something represented by A. Now, if you took a look on your periodic table, and tried to find the element whose symbol is A, you'd look all day and you'd never find anything. A stands for anything. Just think of A as standing for anything. That's a general acid. Without having to specify the exact formula, we can talk about it in general terms. HA, upon losing H, became A minus. The other reactant, H2O, and oftentimes you'll see water involved in an acid-base reaction because everything's aqueous with them, receives an H to become H3O. So HA is our acid, and again, H2O is our base. How about a base? Remember, bases are substances that receive H. Now, in this case, I'm going to use the letter B, and yes, there is a element that has the symbol B, it's boron, but in this case, B stands for base, it doesn't stand for boron. If you're a base represented by the letter B, and your job, according to the Bronsted-Lowry definition, is to accept or receive an H, then you become, on the right side of the equation, BH. The water started out H2O, and upon losing an H to B, it becomes OH minus. Hey, notice that water can be either acidic or basic. It depends on the situation. When it's paired with a base, water acts as an acid. When it's paired with an acid, water acts as a base. We call water amphoteric, meaning it can go both ways. Okay, now let's talk about pairs. Two substances related to each other by the donating and accepting of a single proton is called a conjugate acid-base pair. Let's look at that equation for a general acid one more time. We had identified HA as the acid, and upon losing an H, it becomes A minus. We had identified water as the base, and upon receiving an H, it becomes H3O. Now watch carefully. Yes, HA is the acid, and yes, H2O is the base. But what the acid becomes after doing what an acid does, losing an H, is the conjugate base. And what the base becomes after doing what bases do, receiving H, is the conjugate acid. So bases become conjugate acids, acids become conjugate bases. Isn't that curious? We kind of flip the name of it. HA and A minus form a conjugate acid-base pair. H2O and H3O form a conjugate acid-base pair as well. Now, there's one other thing that we should probably mention here. That's the charge. Notice that HA was initially neutral, and it became, in becoming the conjugate base A minus, it lost 1 unit of charge. If you're losing H plus, the plus goes along with your donation. So your charge count goes down by 1. For the H2O base, upon receiving an H plus, your charge count goes up by 1 as well. So not just are you getting 1 more H, H2O becomes H3O, but your charge went up from neutral to positive 1. Let's talk about these 3 equations. Sometimes it just takes a little bit of practice. Sometimes when reading equations like this, I say we're reading the music. That is, we're reading from the left side to the right side of the equation. And we're trying to pick out things that differ in formula only by an H. So like the difference between NH3 on the left side of the equation in the first one and NH4 on the right side of the equation is only an H. That's your conjugate acid-base pair. That's one of the 2. The other one is H2O, which becomes OH, or you could call that HO if you prefer to write the letters in that order. So the pairs, the conjugate acid-base pairs, are only going to differ in formula by an H. Then, to figure out which one's which, like is NH3 the acid or the base? Well, what I'm going to do is look for the thing that it became on the right side of the equation and ask myself, in becoming that, did it gain an H or did it lose an H? And is that more like an acid, which loses H, or is it more like a base that gains H? Well, in that case, that's a base. NH3 is your base. H2O is your acid. And then one more thing, bases become conjugate acids. Acids become conjugate bases. Your two conjugate acid-base pairs are NH3 and NH4. Notice their formula only differs by H. H2O and OH are also your conjugate acid-base pair. Oops, sorry. Let's look at the next one, HCl. On the left side of the equation, it's HCl. On the right side of the equation, I'm going to look for something that only differs by one H in formula. That would be Cl minus. To become Cl minus, HCl must have lost an H. H2O on the left side of the equation is paired up with H3O on the right side of the equation because their formula only differs by an H. To become H3O, H2O had to have gained an H. So that makes it the base. So HCl is the acid, H2O is the base. The thing that HCl is paired with, the Cl minus, that's the conjugate base. And H3O, the thing that's paired with H2O, that's your conjugate acid. So our two pairs, HCl and Cl minus, H2O and H3O. Last equation, PO4 3 minus and H2O. What's the substance on the right side of the equation that looks like PO4 3 minus, but it only has one, either one more or one less H? HPO4 with a 2 minus charge. That has one more H. And what's the thing that's related to H2O differing only in formula by an H? OH minus. PO4 gained an H to become HPO4. So that means it must have been the base, the thing that gains H. And H2O lost an H to become OH minus, the conjugate base. The thing that loses the H is the acid. The thing that gains the H is the base. And our pairs in this last equation, of course, differ in formula only by an H, PO4 and HPO4, H2O and OH minus. All right, students, with that, I invite you to try the homework. Good luck.